Right. So what we are set to prove now is the strong approximation theorem. So recall that the approximation theorem tells you that the weak approximation theorem that we already proved and used a couple of times tells you that if you have a finite number of prime divisors and a finite number of functions, then there is some other function that can be as close as you wish to each of these functions. You can specify exactly how much you want to get close to, and you get that. But the weak approximation theorem tells you nothing about what happens outside of this finite set, which we denoted by S. So in the strong approximation theorem, we have a stronger version. The stronger means that is manifested in the fact that you can choose one prime divisor all of the poles will go to. So what do I mean? So say you'll have a function field, and there is a finite set of prime divisors, and there is an additional divisor, not one of these, Q. This is kind of like the dummy divisor, or pole prime divisor, okay? And let's say that you, I think there is a little typo here. So this should be S. Sorry about that. So for every prime divisor in your set, let xp be a function, any function that you want, and mp is a number. You should think of it as how close do I want to be to that function with respect to that prime divisor. Then the strong approximation theorem tells you that there exists some function x, such that, as in the weak approximation theorem, for every p and s, your x, the x that we found, that is guaranteed to exist, is mp close to xp with respect to vp. But you know, that's the weak approximation theorem. It looks exactly like that. But in the strong approximation theorem, you are also guaranteed that every prime divisor outside of S and Q, for every such prime divisor, X doesn't have a pole at that prime divisor at that point. So VP of X is at least 0 for every P, which is not those from S and that of and the Q. So this means really, you know, if the MPs are non-negative, for example, it means that the only poles that X it can have, and it will have poles unless it's constant, is at Q. Okay. So it's, you know, it's good to know. It's more kind of controlled. You know exactly where the poles are, and you can manage that, which is quite cool. And to prove that, actually what we'll do, we're going to prove a weaker version. We're going to prove it only with inequalities in the MPs rather than equalities. But then, you know, us in the weak approximation theorem, we also had this step before getting the final result of equalities. And the same trick that we did there for moving to inequalities to equalities works here. So I'll just leave it as an exercise, or you can just see there what happened, and you can see that it's all the same here. It doesn't affect the extra condition. Okay. Okay, so the idea is the following. So we are going to hook up this divisor. So we are going to, for some number n that we're going to specify in a second, we are going to look at a divisor which has m q's, and then you subtract for every prime divisor in S, mp multiples of that. Okay, so we're given all the MPs and S. You didn't use the XPs so far, but given those numbers and the set that's itself and Q, we are going to look at this divisor. And the way we choose M is just large enough so the degree of A is strictly larger than 2G minus 2. Okay, and you can always do that, right? So, I mean, the degree of that is just some number, constant number, because S is finite, and the degrees of the P's is just, you know, each of them is a finite number, and same for MP. And Q is also just, you know, it has degree at least 1. So you can choose M large enough so that the degree of A altogether will be as large as you wish, particular larger than 2G minus 2. So this is just reminding you of what we did. And by Riemann-Roch, we know that the degree of A minus the dimension of A, the deficiency for divisors with such high degrees, exactly G minus 1. Right? Now, if you recall, when we talked about Adels, we proved that if you have a divisor that is maximal in this sense, namely degree minus dimension is as large as it can be, if you have such a divisor, then any addel can be written as an addel coming from the divisor, the lambda space of A, plus some function. So we're going to consider the following particular addel, which will suit our needs and will encode the XPs that so far we haven't used. So the addel will assign the function XP that you got for every P and S and 0 otherwise. Because S is finite, this is indeed an addel, because there could be only finitely many problems, right? Prime divisors in which XP has a pole, because 0 never has a pole. So that's an addel. Right, so this is what we did so far. That's the divisor that we have, and that's the addel we defined. And we know that. And because we know that every addel can be written as an addel in lambda A plus F, then we know that there is some element X such that X minus alpha is in the lambda space of A. Right, so for our particular alpha sits here, then, right, so alpha is here, so you can always write it as, alpha plus something in A, as X plus something in A, something in the lambda space of A. So this means that X minus alpha is in the lambda space of A. And if we break it down, it means that for every prime divisor, VP of X minus alpha plus VP of A is non-negative integer. And so for those P's in S, it means that VP of X minus XP, because alpha at P is XP when P is in S. So minus MP, because VP of A is minus MP, right, when P is in S. This is larger than 0. This is exactly what we want for those primes in S. I think we want this to be larger than the prescribed MP. And for every P which is not Q and not S, we have that VP of X, right, because it's VP of X minus alpha, but alpha is 0 outside of S. So VP of X is at least 0, right, because if you are not Q and not one of these, then A has a 0 in front of the prime divisor that you're considering. Yeah, and that's it.